So Lorenzo will tell us a little bit about, or maybe more than a little bit, about the deformations and the dynamics of the hat family of tilings. Please.
Well, thank you. As the final speaker, it is my honor and privilege to lead the final cheer for the organizers and for the developers. And I thought we should do this the traditional 3 cheers way. So, hip hip, hooray! Hip hip, hooray! Hip hip, hooray! All right. All right. So, what I want to talk about is not just, I don't want to talk about tile. I don't want to talk about a particular decidability question. I want to talk about a family of tilings. And, so we're going to review the very basic facts about the hat tiling, which is not going to take so very long because Craig did that really, really well yesterday. And then Chaim did the same thing later, but, but we all learned that from Craig. And then I'm going to pose a bunch of dynamical questions about the hat family of tilings and provide you with some answers. And the answers are going to be opaque and filled with all sorts of jargon. And so then we're going to do a digression talking about the Fibonacci tiling, in which we can explain what the heck that jargon actually means. We're going to see the process of what happens with the hat tiling in a similar one-dimensional setting. And once we understand what happens with the Fibonacci tiling, then we can go back to the actual proof of the answer, and that's going to involve cohomology. And I claim that tiling cohomology is the best thing since sliced bread. Everybody should be using cohomology. Sir Roger mentioned cohomology as this fancy stuff that we weren't talking about. No, we're going to talk about cohomology. Okay? And then, what about the Spectre? That's, every question you can ask about the hat, you can also ask about the Spectre. And so we're going to see what the answers are for the Spectre tiling. Fair enough? We ready?
Mm-hmm.
Behold the hat. There is the hat tiling, and we've seen this, and we've loved it, and we noticed that all of the what is this? Not pointing at anything.
I think the screen eats a light.
There we go. And we see that all of the anti-hats are shaded, and they form something close to a hexagonal lattice, but not really a hexagonal lattice. And you've all seen a much better picture of the hat, under the stairwell that we've all helped to construct. And hooray for us, we won't go with the 3 cheers anymore. Okay? So, what are the ingredients of the hat tiling? Well, you have the hat tile. And it's a particular tile, and it appears in 6 different orientations. It appears, and then it appears rotated by 60 degrees and 120 and 180 and 200 and 240 and 300. And you also have the anti-hat, reflected, appearing in 6 orientations. So if you're doing things up to translations, there are 12 tile types out there. If you're doing things up to Euclidean motions, there's only one type. It's a monotile. Hooray for monotiles. No, you don't have to. Okay? And we're looking at a particular setup here where there are more hats than anti-hats. You could also reflect the whole thing and have more anti-hats than hats, but the structure of that is just like the one where you have more hats than anti-hats. So we're just going to concentrate on the tilings where you have more hats than anti-hats. Okay? Now, there is our basic hat. And I happen to draw it with the particular convention that, the length of the thing we call the hat. But really, you could build this shape. I mean, you have these red tiles that have length square root of 3 over 2. And you have these blue edges that have length 1/2. And this big, long blue edge is really 2 short blue edges concatenated. And that is the basic shape. And you notice that the red edges are pointing in the horizontal direction plus multiples of 60 degrees. And the blue edges are pointing in the vertical direction plus multiples of 60 degrees. So, but what would happen if we took these red edges here, these two, and made them longer? And likewise, at every single tile every single tile has two red edges pointing at 60 degrees above the horizontal. And we made those longer too. Well, every tile would get stretched. And of course, a 60-degree angle red edge can only touch another 60-degree angle red edge. So if you stretch both of them, you don't get any shearing. And since there are two red edges on each face, you don't change the fact that the sum of the edges around a face gives 0. So everything keeps fitting. You just distort the tiling in that vaguely northeast direction. Now, in the process, you've broken rotational symmetry. We don't like to do that because we want to have everything being a single monotile. So as you stretch out the red edges, these red edges, you also want to stretch out these red edges, which come in pairs. You want to stretch out these red edges that come in pairs. And the whole thing works as long as you just make all of the red edges have the same length, and all of the blue edges have the other length. And I was about to say that the red edges were A and the blue edges are B, except that I noticed that my convention for tile of AB is opposite the one in the paper, and they've got priority. Yeah, that's only fair. I have to switch my convention. So A is the size of the blue edge, B is the size of the red edge. Blue edges go vertical plus multiples of 60, red edges go horizontal plus multiples of 60. Okay. So here are some examples.
B for blue.
B for blue, okay. So we have the chevron where the blue edges have size 0. We have the hat where the blue edges have 1 over root 3 times the size of the red edges. The proto-spectre where they have the same size. The turtle, and it doesn't look like a turtle, but if you rotate it 180 degrees, it really looks like a turtle. Where the blues are root 3 times the reds. And the comet where the reds have disappeared and it's all blue. Okay? And you could, we saw the movie that Craig showed us yesterday of how you can take a tiling by any one of these and deform it into a tiling by any of the others, that all these shape changes just behave very, very naturally. Now, as it happens, there's no reason that those shapes need to be real. Instead of saying, I've got horizontal by a length B, from your perspective, horizontal plus a length B plus multiples of 60 degrees, I could just take any complex number plus multiples of 60 degrees, or rather, times any sixth root of unity, because I'm going to think of R2 as being the complex plane. And likewise, I have IA, well, if A is real, it points this way, but if A is complex, maybe it points this way, times any multiple of 60 degrees. So my parameters A and B aren't two real parameters, they're really two complex parameters. Now there is one hitch there. If I use tile AB, then for the other-handedness, I can't use the reflection of tile AB. I have to use the reflection of tile A bar, B bar. And of course, if A and B are real, then you get the same tile up to reflection. It's a monotile, everybody's happy. But if A and B are complex, then you have two tiles that are no longer isometric. So if what you really, really care about is monotiles, 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 this is bad. If what you care about is, here's an interesting tiling, let's see what the structure of this tiling and these tiling spaces look like, then you're fine with it. Okay. So here's the deal of why you need the bars. If you have A and B real, then the reflection, this is part of the boundary of a tile. And you can see that the reflection just fits in neatly. you fit it, you don't rotate to match this to this, you rotate by 60 degrees 3 times to match this to this, everybody's happy. If you have A being complex, then its reflection doesn't fit. You can't fit this to this without rotating by some funny small angle. You can't do it by multiples of 60 degrees. And if you did rotate by some funny small angle, then this would no longer fit this. Right? This is an angle that's a little bit bigger than 90 degrees. This is an angle that's a little it's a little bit less than minus 90 degrees, and a little more than plus minus 90 degrees is not a multiple of 60 more than a little less than negative 90 degrees. Instead, you need to use A bar, B bar. So if you want to have this in the picture, you put this, the reflection of A bar, B bar, not the reflection of AB. The reflection of AB doesn't work. The reflection of A bar, B bar does. Okay? So now we know what kinds of shape changes we're talking about. So what we want to know is, well, what about the dynamics? What are the dynamics of these tilings? So if I, for example, if I give you one of these tilings and say, hey, what is the diffraction spectrum look like? Or if I look at a tiling space and I say, okay, what's L2 of the tiling space? What is the action of translation on that tiling space? What is that dynamical spectrum? And do the answers depend on A and B? It's not obvious one way or another. Now, if you look at the chevron comet, the chevron tiling, all the vertices live on a lattice. And since all the vertices live on the lattice, the dual lattice has to be part of the spectrum. Okay. If you look at the comet tiling, all the vertices live on the lattice, so the dual lattice has to be part of the spectrum. But as Craig explained yesterday, those lattices are incommensurate. One of them has half the area per unit cell of the other. That's weird. They're related by the factor of golden mean minus psi to the fifth, where psi is the sixth root of unity. Psi is 1 plus I root 3 over 2. They're related by this funny complex number whose argument is the arctangent of 3/5, which is just a weird number, a weird irrational angle, and you've got this funny twisting going on. Okay, so those are the questions. You want some answers? Should we just call it a day? Okay. Oh, some answers. Changing A and B doesn't matter. Up to an overall rotation scale, all spaces are topologically conjugate, which means that there is a map. If you give me one pair of values of A and B, and you give me a different value of A and B, we've got these tilings and these tilings, and I may have to rescale them, and I may have to rotate them, but after I've done that, I can give you a map from this space to this space that commutes with translations and preserves all the combinatorics. So as far as the dynamics goes, they're the same dynamical system. They have the same spectrum. They have the same properties. They're to a dynamicist, they're the same. You do diffraction off of them, you get the same Bragg peaks. You don't get the same intensities, but you get the same Bragg peaks. Okay, so the claim is they all have, and in particular, that spectrum is pure point spectrum. And what is the spectrum? Well, it's a constant times the integers with the sixth root of unity adjoint and with the golden mean adjoint. And so, in particular, it contains phi minus psi to the fifth. So multiplying by psi minus 5 to the fifth leaves you within this space. And now, within this big space, those two lattices are no longer incommensurate. Okay. They're all cut and project tilings. Anything that has pure point spectrum can be expressed in via a cut and project construction. In this case, it's a projection from 4 dimensions down to 2 dimensions. Okay? And that has a very nice window, which I'll show you in a minute. And all of these different tilings, with all these different values of A and B, they have the same total space. They have the same set of points in the same total space. The only thing that's different is the way that you project from this 4-dimensional space to 2-dimensional space. So they're all reprojections of the same set in 4-dimensional space. So all you're doing is a reprojection. And there is a self-similar tiling within this thing, which we call the cap tiling. And I forgot to bring my cap. I was going to put a cap on. But cap, of course, it's a kind of hat, but it also stands for cut and project. Okay, so that's why we call it a cap tiling. And it's self-similar, and self-similar models are very nice, that they have particularly nice analytic properties. So what is this cap tiling? Well, we saw yesterday that you can express the hat tilings in terms of these metatiles. There's the little triangle. Where's the little triangle? There's a little triangle. There's a hexagon. The little triangle T, a hexagon H, a parallelogram P, and this funny guy F. F can stand for fulvet, or it can stand for funny guy, or it can stand for a bunch of things. Okay? And what we're going to do is we're going to get a control point associated with every single point. Now, the way we chose the control points is they're not necessarily in the corresponding tile. So here we have an orange, a mostly orange T tile, and there's the control point for that T tile. There's the control point for the H tile. This control point, it's purple. It refers to, I think it refers to this tile. And if you choose the control points properly, you get that the return lattice has a bunch of nice properties, and this whole thing is self-similar. That if you do a substitution, all of the spacings between control points get multiplied by exactly golden mean squared. It's not just combinatorial, it's geometric. Everything just literally scales by golden mean squared. Okay, and there's the window. It's a pretty window. It's just a hexagon, and it has, you can either say 4 or 24 pieces that, these are the guys that go to the purple points. These are the guys that go to the red points. Now, this refers to triangles in one orientation. This refers to triangles in different orientation. This in a third, and a fourth, and a fifth, and a sixth, because every tile appears rotated by multiples of 60 degrees. And there's the window, and it's got fractal, most of it has fractal boundaries. But the entire window is just a hexagon. Pretty darn simple. Okay, so some more results. If you have a tiling space that is homeomorphic to the cap, in other words, and all of our tile AB hat tilings give a space that's homeomorphic to the cap. But if you drag in something off the street and say, you know what, this guy is homeomorphic to the cap too, in fact, it is up to topological conjugacy. It's conjugate to a linear transformation applied to the cap, and therefore it's locally equivalent to a linear transformation of a reprojection of the cap. In other words, it's basically a tile AB tile. There's nothing new. If you look at all of the things that are homeomorphic to the cap tiling, it's the things that you already knew and nothing extra. There's a sort of topological rigidity to the whole game. Okay, so I've told you topological conjugacy. I've told you reprojection. I haven't told you what any of that means. That's kind of a problem. So we're going to look at Fibonacci tiling. Fibonacci tiling, it's a nice one-dimensional tiling. It's a cut and project tiling. And it's a tiling where you can imagine the shape changes very, very easily. So it's a substitution tiling, which you can think of as replacing A with AB and B with A. Or you can think of it as a fusion tiling, where you have groupings that are bigger and bigger and bigger and bigger. And at the n plus first stage, the n plus first grouping of type A is built by taking an nth order grouping of type A and concatenating it with an nth order grouping of type B. And an nth order grouping of n plus first order grouping of type B is just A. Okay. So everything builds into bigger and bigger and bigger clusters. And if you look at the substitution, well, A goes to AB, so 1A, 1B. B goes to A, that's 1A and no B's. You've got that matrix. Eigenvalues are the golden mean. Eigenvectors are phi 1 and 1 negative phi. The right eigenvectors and left eigenvectors are basically the same. In general, right eigenvectors have to do with columns, have to do with the frequencies of different kinds of vectors. Left eigenvectors have to do with the size of the different kinds of tiles. Okay. And if we want to understand shape changes, we're looking at sizes. So we're looking at left eigenvectors. So if I tell you how big I want, there it is, how big I want A and B to be, you could always decompose it into a linear combination of the two eigenvectors. And then you see what happens under substitution. Well, this coefficient gets multiplied by powers of phi. This coefficient gets multiplied by powers of 1 minus phi. And I claim that two length choices have the same coefficient of the big eigenvector, then the corresponding spaces are topologically conjugate. You can come up with a map between them that commutes with translation. Okay, so we're going to look at that. We're going to look at two cases. We're going to look at one case which is self-similar, where A has length golden mean and B has length 1. And we're going to look at another case where A and B are the same length. And I want it to be the same, these guys have an average length of phi squared plus 1 over phi plus 1. So we're going to give these guys that average length. And it happens that if you take phi squared plus 1 over phi plus 1 times 1, 1, that is phi 1 plus this multiple of 1 minus phi. If you ask how big are the super tiles, you just hit it on the right with the substitution matrix. So in one case, you have phi 1 and you just multiply by phi to the n. In the other case, you have phi 1 that you multiply by phi to the n, and this other piece that you multiply by 1 minus phi to the n. And 1 minus phi is negative 0.6 something. It's less than 1. You take powers of that and things shrink. What that means is that even though these tilings have tiles that are different sizes, asymptotically, their super tiles have the same size. And so we call this difference asymptotically negligible. So how would we build a conjugacy by, this is going to be tiles in the tiling space where they have length phi and 1. And this is going to be tiles where they have length the same. How would you build a conjugacy with that? Well, you could try to line up the vertices, map something where the vertex is here to something where the vertex is here, map something where the vertex is here to something where the vertex is here. But that's not conjugacy. Because when you translate by this much upstairs, you're translating by less downstairs. You translate by this much upstairs, you're translating by more downstairs. It's a map, it's a homeomorphism, but it isn't conjugacy. Or you could try to line up the vertices of the first order supertiles. That still isn't a conjugacy, but there's less distortion than there was when you were doing tiles. You line up, you map the vertices of the first order supertiles to the right places, and you linearly interpolate in between. If you do a second order supertiles, you do even better. You do a third order supertiles, and if you squint really hard, you might be able to see that there's some distortion. You might be able to see that this supertile is a tiny bit longer than this supertile. Or maybe it's shorter, I forget which. I can't really tell by looking at it. Okay? They're really, really close. And you have these maps that map on vertices and linearly interpolate in between, and you can take the limit. The limit of these maps commutes with translations. That's your topological conjugacy. So if you have the structures, you have these higher order supertiles asymptotically have the same size, then the tiling spaces are topologically conjugate. Nice, huh? Okay. You can also see the same thing by reprojection. One way to get the Fibonacci tiling is by a cut and project scheme. You take a lattice in a higher dimensional space, and you take a strip here, all the ones whose antennas reach your line of physical space. And then the ones that are close enough, you project onto physical space. And this displacement in 2 dimensions is given by the vector 0, 1, but when you project that difference, you get a small distance. In physical space, this separation is 1, 0, and when you project down to your line of slope, 1 over the golden mean, you get a longer distance. What would happen if we took the exact same points and instead of projecting in this direction, we projected along a slightly different direction? If I change the axis of projection this way, this distance will get bigger. This distance will get shorter. In fact, you can take it, push it far enough. I'm using the exact same points, the exact same cut and project system. I'm just using a different projection. Erase the first line, and now you see that all of the separations are the same. The length of an A tile is exactly the same as the length of a B tile. So that's what I mean by reprojection. So the claim was that with the hat tilings, if you change A and B while keeping the average size the same and tilting them appropriately, that you're getting a cut and project set with the exact same window, only with different projections. Okay? So, now that we know the results, why is it true? And the answer is cohomology. Now when I say cohomology, that's your invitation to run screening from the room. If you don't like algebraic topology, you're not running. Yay! Okay, you're not running. I like this. And so you have this theorem that Alex Clark and I proved back in 2006 that says that if you want to take any tiling space and you want to understand what are all the possible shape changes up to local equivalence, MLD is just a mutual local derivability, and MLD star is MLD that preserves the combinatorics. Things up to local changes are classified by cohomology. What cohomology? Well, it's the Cech cohomology with values in RD. That's the Cech cohomology. Now, you're still not running from the room. I'm doing well. Okay. Now, for substitution tilings.
There you go.
Okay. That's happening.
Too many threats.
In substitution tiling, there's a subspace that doesn't give you local equivalence, but that does give you topological conjugacies. And those we call the asymptotically negligible guys. And you can get those by looking at how substitution acts on the cohomology and looking at the contracting subspace. And those are the asymptotically negligibles. So this is the theorem from, 17 years ago, when I had a little bit more hair. Well, I had some. I had some. Okay, so if you do this with Fibonacci, you get that the cohomology is 2-dimensional, and the eigengenerators are the indicator function of an A tile and an indicator function of a B tile. And those substitute by the same old substitution matrix. Eigenvalues, golden mean, 1 minus golden mean. Contracting subspace is the 1 minus the golden mean. And you get that's this eigenspace, which I said you vary the lengths by this much and you get a conjugacy. And the other direction, well, what happens if you take something with size phi 1 and you vary its shape by a multiple of phi 1? Well, it's not a conjugacy, But you just made it bigger. You made it bigger without changing the shape. That doesn't change anything qualitative about the dynamics. So the upshot is that every Fibonacci tiling for every choice of A and B is topologically conjugate to every other Fibonacci tiling up to an overall rescale. And you get that by just seeing that the cohomology has rank 2, and one generator is rescaling and the other one is topological conjugacy. And that's all there is. Okay. Now the other thing you have is something that I proved with Antoine Julien back in 2018, is that every homeomorphism between tiling spaces with finite local complexity is homotopic to one of these shape changes that we talked about, followed by an MLD equivalence. So if you want to understand all homeomorphisms, not just shape changes, well, they are basically shape changes. So if you understand the cohomology, you understand everything. Okay, so now what does it tell us about the hat? Well, R2 is, we're looking at things in the plane. So we say, when I say with values in R2, I might as well be saying with values in the complex numbers. So we're looking at the complex value cohomology, and the answer decomposes into two pieces. One of them gives linear transformations. The other one is asymptotically negligible, just like Fibonacci. So how the heck do we compute this cohomology? Well, this is a procedure that was developed 25 years ago by Anderson and Putnam. And the rule is you basically take one copy of every kind of tile, and you glue them together along ways that they can possibly meet. So if somewhere in the tiling, this kind of tile meets this kind of tile along this edge, then you identify this edge of this tile with this edge of this tile. So you wind up with a complex that is just a bunch of faces glued together along edges. And you then compute the cohomology of that thing, and now you don't need to worry about Cech cohomology, because with simple complexes, every kind of cohomology is the same as every other kind. So if you like to do simplicial, do simplicial. If you like to do cellular, do cellular. If you like to do singular, do singular. They're all the same. And then the substitution maps this space to itself, and you look, and so maps the cohomology to itself, and the space is the inverse limit of this complex under substitution. The cohomology of the space is the direct limit of the cohomology of that complex under substitution. Okay? So now let's look at what you get for the hat. Well, Craig told us what kind of faces you have with a hat. You have 4 kinds of faces, T, H, F, and P, or P and F, or whatever. Whatever order you prefer, and each one appears in 6 orientations. Now, if you're masochistic, you will think of that as 24 different kinds of tiles. I prefer to think of it as 4 kinds of tiles, each in 6 orientations. So I'm going to have T, RT, R squared T, R cubed T, R to the 4th T, R to the 5th T, H, RH, R squared H, etc., where R means rotate in the positive direction by 60 degrees. And then there are 5 edge types. 4 of them have a direction, and so come in 6 orientations. And one of them doesn't have a direction, so if you rotate it by 180 degrees, you get the same geometric set. But if you were going this way and you rotate by 180 degrees, now you're going the other way. So R cubed times that L tile as a chain is minus the L tile. And then you have 3 vertices that you work out. X minus means the back end of an X, F minus means the back end of an F, X plus means the front end of an X. And those have some relations. And you can work out the boundary maps. So if you want to know what is the boundary of this guy, this is an A tile. The convention is that an edge, standard orientation for an edge is pointing up with the markings on the left. So, whoops. This is an A tile rotated clockwise by 60 degrees, that's an r to the fifth a. This is an r to the fifth, this is an ra, and this is minus a b, because it's actually a b, but since the boundary, you take this plus this going down. So the boundary of this guy is just r plus r to the fifth a minus b. And you can likewise work out that the boundary of this is r plus r to the fifth b minus a, and all of these green guys, which are x's, cancel. And you figure out the boundary of this, you figure out the boundary of this, and you get the matrix for the boundary map. The boundary of a t is an r plus r to the fifth a minus a b. The boundary of an h is minus an a plus an r to the fifth b, etc. And the key thing is that everything commutes with rotation. So you don't have to do this as, think of this as a 12 by 20 and a 20 by 24 by 16 matrix. 30 by 24 matrix. You can just do it one representation at a time. And what are the representations of six-fold rotation? 6 roots of unity. So you just plug in r equals 1 and you do a calculation. Then plug in r equals the 6th root of unity, do a calculation. Plug in r equals that squared, do a calculation. Plug in that equals r cubed, do that calculation. The only subtlety is that because of this relation, you only get the L edge in representations where r cubed is -1. So if you, in the r equals 1 and r equals psi squared and r equals psi to the fourth representations, you just don't have any L's. And likewise, you only get these vertices in the r equals plus or minus 1 representations. And you get this vertex this vertex in every representation. You write down your matrices with the understanding that certain rows and columns just don't exist in certain representations. And you do your calculations. And all you need to do is just keep track of the rank of the different matrices. And there you have it. So, for example, in the r equals psi representation, you have 4 faces and 5 edges and 1 vertex. Well, the rank of boundary 1 is rank 1, so that you don't get any h0. And the rank of boundary 2 is 2. Well, 2 plus 1 is 2 less than 5, so h1 is 2-dimensional. You just have to look at the ranks of these matrices. It's not a hard calculation. A little bit grungy, but it isn't hard. And so then you rattle off what the cohomology is. And there you go. You get a c squared in the fundamental representation and a c squared in its algebraic in its complex conjugate. And that's all there is. Okay, that's of the complex. We actually have to take the limit of that. I'm not going to show you that. All of the matrices are invertible. Nothing changes. Okay, we're running out of time. Okay, so the punchline is you've got the C4, 8-dimensional family of shape changes. The eigenvalues under substitution are the golden mean squared. The big eigenvalues, those are linear transformations. You have a C squared for that. All linear transformations of the plane can be written as z goes to some number times z plus some number times z bar. So those are linear transformations. The other guys, 5 and minus 2 is less than 1. Those are topologically conjugate. Everything is topologically conjugate to a rescaling of everything else. There's only one game in town. Okay? Now, there's a particular ratio that gives you self-similarity. That means that your cohomology class is the eigenvector. And that's what you need to do the cap tiling. And once you have something self-similar, then there are a whole bunch of tools that you can bring to bear. Now, I don't know these tools very well, but Franz and Michael know them really well. So you turn to Franz and Michael and say, hey, we've got this self-similar tiling. What are its properties? And they say, aha! It's, thanks to the overlap algorithm, we know that its spectrum is pure point. And That makes a cut and projectiling, and we choose the right control points and then mapping it to perpendicular spaces, just taking an algebraic conjugate, and so we get all these points and we get this really pretty window. And isn't this a wonderful thing? And the reprojections, how many reprojections are there? Well, the space of projections from 4-dimensional space to 2-dimensional space, the dimension of that is the codimension times the dimension. 2 times 2 is 4. How big is H1? The contracting stuff? 4-dimensional. Oh yeah. So all of our asymptotically negligible shape changes they're the exact same thing as reprojections. Okay? That's it for the hat. So what about the spectre? Well, there it is. It's pretty. Well, with the spectre, what are the ingredients? You have 12 tiles up to rotation. And originally it's just these deformations of tile 1, 1. And with 6 orientations more common than the other 6. But you can also deform things. Basically, you get something with A's horizontal and IB's vertical plus 60 degrees. And the other one has A's vertical and B's horizontal up to multiples of 60 degrees. And if you want, and one of them is rotated by 30 degrees relative to the other. If you want them to match, you don't need to have A equals B. What you need to have is AB for one set and BA for the other set. And this time, of course, if A is not B, then you have 2 different tiles. It isn't a mono tile. Okay, fine. But if you're going to change things, there's no reason not to change things in the complex direction. Right? There's no advantage to real changes over complex changes. So we can take A and B complex and our space of deformations. It's C squared just like with the hat. So same song, different verse. The cohomology winds up being C to the 4th. Those of you who were in Milton Keynes, we said the cohomology was C to the 10th and then found a mistake in the calculation. Sorry about that. Okay, you don't have the golden mean squared as your stretching factor. You have 4 plus the square root of 15 as your stretching factor. Yeah, so what? It's a PD number. Basically, it behaves the same. The second C squared is less than 1, so it gives you topological conjugacies. The big guys give you linear transformations. So all of the spectre families are conjugate up to a linear transformation. So that's what we know. But there are a few things that we don't know. So we know that the point spectrum is always of the form Z with the 6th root of unity and the stretching factor adjoined. What we don't know is that it's pure point spectrum. We haven't gotten around to doing the overlap algorithm and the mappings and the density arguments and so on and so forth. This is work in progress. We expect that it's pure point spectrum, and if it is, then it's a cut and project set. Okay? If it's a cut and project set, well, what does the window look like? Probably something vaguely hexagonal, but we don't know. Okay, and then we also had the fact that for both the hat and the spectre, the cohomology was the smallest it could possibly be. Does that reflect some particular structure to the hat tile itself? Maybe. We don't know. It's an interesting question and we're working on it. Okay. The spectre is written as a substitution involving 9 hexagons. You can do it with 2 tiles, but then it doesn't force the border. If you want to have proper topological control, you need 9 hexagons. Can you simplify that? Yes, we've got it down to 7. Can you simplify it more? I don't know. And then we have some general things. Suppose that you have some monotile that isn't the hat and isn't the spectre, isn't in the family. It's something that's going to be discovered next week.
By day.
What?
By day.
By Dave, of course by Dave. Who else? Will it wind up having pure point spectrum? Right? Taylor Socolar has pure point spectrum. The hat has pure point spectrum. We think the spectre has pure point spectrum. Is that a general property of monotiles? We don't know. It's an interesting question. And if you have a monotile, does it have to generate something hierarchical? Well, all the examples so far do. Does it always? We don't know. So, morals of the story. All Hat family tilings are basically the same. All Spectre family tilings are basically the same as each other, not the same as the Hat. And how do you understand both of them? The key tool, that is cohomology. That drove a few people screaming for the room, but the rest of you stayed. You should learn to love cohomology. And in particular, in both families, H1 was absolutely the smallest it could be. It has to have an expansive right two direction just because you're in two-dimensional space. You have to have the other two directions because of algebraic conjugacy. So it was as small as it could be. And that was what happened. And we don't fully understand the Spectre the way that we do the Hat. We don't have a picture of the window, for example. We're working on it. And I'll stop there.
Thanks, Lorenzo. Questions, comments? Dan.
So you said that H1 is as simple as it could be, but H2 looks a lot more complicated.
It does. It is a lot more complicated. For the Hat, H2 is 10-dimensional and has contributions from, I forget if it's all the representations or almost all the representations. So it's a lot more complicated, and so that gives you things like, ways to count tiles. In particular, the component in the fundamental representation, the r equals 6√1 representation, is what gives you the fluctuations in populations relative to what was coming up in Daniel's talk. And likewise, we get there's a piece of H2 for the Spectre that transforms with eigenvalue 4 plus root 15, while the main thing is doing 4 plus root 15 squared. And we don't really understand what those classes are telling us. We know they're there. We don't really understand what is their deep significance. A few of them we can basically say, oh yes, this one is counting, tiles up to rotation. For example, if you put an arrow on every tile and rotate a tile gets this arrow, that you're adding up the arrows. That's what some of the classes are doing. What are the other classes doing? We don't know. I mean, we can write it down, but we don't have any intuition about what it means. At least I don't. You guys? And it was on my opening slide, but I never said it explicitly. This is all joint work with Michael and Franz.
Other questions or comments? Yes.
You did the projection thing for the Fibonacci regression. Is it possible for other substitutions where you get same length?
Basically, if you ever have a cut and project tiling, there's always a bunch of reprojections you can do. That there's a space of reprojections whose dimension is the codimension times the dimension. So you have these reprojections, and these are never MLD equivalences, and they are always topological conjugacies.
Not now you question what is MLD?
MLD means there's a local map that says, over this tiling you have this picture, down here you have this other picture in the exact same spot. Okay. So there's these reprojections always give you changes that are not MLD, but that are topologically conjugate. Now the question you might want to ask is there anything else out there that gives you a topological conjugacy? Depending on whether we're talking about substitution tiling, if it's also substitution tiling, we can say what are the things that give you conjugacies? It's the contracting subspace of H1 under substitution. if it's a cut and project with a nice window, we can basically say, oh, it's only the reprojections. In general, it's hard to say what are the asymptotic and negligible cuts. So maybe it's just the reprojections, and maybe there's something else.
Yeah, actually, I might like to add that in symbolic dynamics, there's no distinction between, or finite alphabets say, no distinction between MLD and topological conjugacy. So this is really the point where you see that in general tiling theory, things are more complex but also more interesting because you have these topological conjugacies that do not come from a local map.
Which is very different from what we learned from Rachel. Right, that there everything came from discrete structures.
I think there's a question behind it.
Oh, yes, right.
In the cut and project window, you get 2 green circles in this.
Hold on a second.
Does that have any significance? Or is that
Oh, there we go. There's the window.
so you get the green circle at the tip of the purple. Yeah.
You mean this guy?
No, all the way around. Go all the way around green. Keep following? No. Well, that's a circle too, but I mean.
Oh, we have a circle here, and you have all those circles in.
That one, and then all at the tips of the purple triangles. You can go all the way around the whole hexagon. I think. Is that interesting at all, or is it just a curiosity?
I don't know. That's kind of cool. I mean, you have that at different scales.
Yeah, that's
Yeah,
relevant.
exactly.
And those scales are all related by golden mean squared.
Oh, yeah.
Because, it's the structure of these fractal bits. You take this little bit, you scale it by golden mean squared, you get this bit. You scale that by golden mean squared, you get this bit. You scale it by golden mean squared, you get this bit. You scale it by golden mean squared, oh, you're outside. But you can go down and you get little, tiny pieces down here. And likewise for the green, this scales to this, scales to this, scales to this, sort of. Except for the bit that would then be outside. So these, there's a lot of, they have a lot of cool structure, but this was generated, and likewise here you have a little bit bigger bit. But these are basically generated numerically. What you do is you take a big patch of your tiling, and for every point is a linear combination of 1 and 5, of 1, the golden mean, the 6th root of 1, and the 6th root of 1 times the golden mean. You take the algebraic conjugate and the complex conjugate. And that gives you a point in perpendicular space. And so you just collect what all the points in perpendicular space are, and you discover that, hey, all the purple guys land in these 6 hexagons. All the green guys land in this region. All the blue guys land in this region. All the red guys land in this region. And now you have your window.
To say a bit more what you said, these circles, where the points where they meet, they will correspond to singular points. So that will be points where whether you have it or not will depend on which direction you approach it. Yeah. So it will probably say something about the structure of points of a hexagon in the elements of the same fiber over the
I
MEF.
think so. It might be like the points where they're mapping 2 to 1 or something.
Yeah, no, multiple to 1.
Yeah, multiple one.
Cool.
Man, Natalie. Oh, who was first? I didn't see. Natalie.
I was just to keep on the window here for a minute. So we have one of the tile types is associated with those purple triangles, and then the rest of them are fractally. You guys have looked at a lot of window pictures before. Do you see a lot of them where there's like polygons and fractals, and is there any significance to that you've been able to figure out?
You see, the point is that for the boundary, the window itself you can get as an as the unique fixed point of a contractive IFS.
Right.
Yeah, and that would be the alternative way to produce it. The method that Lorenzo describes is just a quicker way to get it, but we know this other guy exists because it's a contractive IFS. And to get the full understanding of the boundary, you have to derive the graph-directed iterated function system for the boundary. That is already a pretty nastily complicated process for 1D substitutions. And for higher D substitutions, it's even more complicated. And these graph systems, they are so complicated that it's imaginable, but we don't know how to analyze that you have subsystems that behave differently. And that could explain why you have both line segments and fractal segments. Wherever it's fractal, it has the same dimension. We've calculated that. And the other one, of course, has dimension 1. But that needs to be analyzed. But these IFS in higher dimensions, they are very little studied. So not even in Bernd's thesis is anything about that.
Yeah. Although we'll point out one thing that the purple things correspond to the fulfits or the triskelions. What was that? Triskelions. And to some extent, they're anchoring the structure of the hat tiling with the fluctuating stuff everywhere else. That this basically says that the structure of those triskelions is in some ways more regular than the structure of the other stuff.
And this fractal nature is also the reason why at the moment the pictures on diffraction that you see are not exact pictures. They are numerical approximations done on big finite parts. But when you have fractal boundaries, these things converge rather slowly. Yeah, so they will qualitatively be correct, but quantitatively they will not. So that the positions will be right, but the intensities will not. Yeah.
Is there any research you've gone into deriving custom object sets for hat tiling from different total spaces? Is there any motivation behind needing to do that? So once you've found one, does that kind of give you all the nice properties you want?
Well, I mean, there's one. I mean, there was this construction by Josh Socolar, which basically got it going from 6 dimensions to 2 dimensions. But that basically says that there is really you can project from his 6 down to 4 before you go down to 2. So that it's not a minimal thing. The exact structure of the window depends on how you choose the control points. And do you want to say something about that, Franz?
Yes. Josh Socolar lifted a certain subset of the vertices of this metatile tiling, and these happen to fall into 4 orbits under the return module. And so you can lift those 4 kinds of vertices to 4 cosets of 4-dimensional lattice, but Josh somehow preferred to choose a higher dimensional lattice to accommodate those 4 cosets. But I think this is not the optimal way to do it. So it has really advantages if you choose control points lying in a single orbit, because then you have a single coset. You can directly lift it to 1 lattice, and the choice of the control points, the solution I chose is not the only one. If you take other choices, this window may fall apart and consist is no longer connected and consists of several shifts. So these different parts can be shifted around if you choose different control points. So this is a particularly nice solution, but not the only one.
But it's still MMD.
Yeah, sure.
Yeah, that is the underlying message here. The tiling intrinsically knows and tells you what its underlying lattice is. And that comes from the return vectors. And if you go to the self-similar point, the return module is easy to determine because you only have to look for the return vectors for the tiles. Because on the next level, it's super tiles. But that's self-similar, so it will produce the same return module. Yeah? While if you would do it for the original head, you would look for return vectors for something, and then you would look for return vectors for bigger patches, and only in the limit you would recover this guy. So that's why the self-similar member in the family makes many things easier.
Well, I would say the return vector isn't so bad. What you need to look for is loops in the Anderson-Putnam complex. You find the loops in the Anderson-Putnam complex, and you say, oh, given our shape, what is the length of those loops? And what are the generators of H1 of the Anderson-Putnam complex, basically? And it isn't too bad, but it certainly is simpler when you have self-similar. You can do it when it's not self-similar, it's just a little bit more complicated.
So maybe this is a good point to wrap it up.
Yes,
I'm happy that we had a fantastic meeting, and I would like to add once more to thank the organizers for putting it together. And thank Lorenzo for a fantastic finale.
That's all, folks.
Well,